Anybody have any questions from yesterday? Yesterday we actually went over externalities, and hopefully you now have a feeling of what externalities are, and I just explained off the camera what competitiveness is, which has all kinds of externalities: economics, political, social, versus productivity, which is how well you can manufacture something or make something. Okay. The other thing that I wanted you to be aware of from yesterday is you have to be quantitative to be scientific. And here actually is the framed quote that's on the wall as you enter my office, except it's not there, it's right here right now. But Lord Kelvin said, I often say that when you can measure what you're speaking about and express it in numbers, you know something about it. But when you cannot measure it, when you cannot express it in numbers, your knowledge is of a meager and unsatisfactory kind. It may be the beginning of knowledge, but you have scarcely in your thoughts advanced to the stage of science, whatever the matter may be. So when you go out there in the real world and people find out, oh, you're from MIT, there's two responses, and most of you have already seen them. Oh, you're from MIT, you think you're hot stuff, huh? So people have seen that. Other people, oh, you're from MIT, you must know everything. Okay? And there's some things in between too, but a lot of people either look at you with disdain for no good reason, or look at you as if you were some sort of savior of the world for no particular good reason too. But you are more qualified than most of them. Okay, so today I wanted to ask you, we're going to discuss the number one factor in selecting materials. Remember, selecting materials is supposed to be what these few lectures are about. And yesterday we talked about the externalities in selecting materials. What is the most important driver in selecting any material, whether it's a silicon chip or whether it's a piece of steel for a bridge, whatever, it could be a piece of nickel-based alloy, right? You're working on nickel-based superalloys. Why don't we build bridges out of nickel-based superalloys? Yeah, so the number one driver is something called price or cost. And that cost and price has lots of externalities in it. Okay, so far as that goes. But it does have some things that are sort of fundamental. And there's a book that I could use this as a textbook. It's called Engineering Materials 1. There's an Engineering Materials 2 by Michael Ashby, who used to be a faculty member at Harvard, and then he went back where he came from Cambridge, and now he's retired. But he developed something that we'll show in a little bit called Ashby Plots. Some of you may have seen them. He's got a company called Granta that has a $50,000 computer program, so you can input your different properties you want to achieve, and it will help you select your materials. Okay? So the second chapter in that is about price and availability of materials, and you can read that. But so far as availability, you can look at it at lots of different levels. One of the things Ashby has, and this is a plot from that handout, which you can't read very well like that, but oops. So this is the abundance of materials in the Earth's crust. Okay? It's not just the whole world. It doesn't include water necessarily, because you would think, well, it does have oceans, and atmosphere. So he has a crust, oceans, and atmosphere. And obviously, it's not surprising, oxygen is number one in the ocean, and hydrogen is number two, even though there's twice as many hydrogens as there are oxygens. But he's doing this on a weight basis, obviously. In fact, it says weight percent at the top. In any case, aside from those little trivial details, silicon, aluminum, iron, calcium, and you could say, well, these are the abundance, and in fact the geologists and geophysicists have figured these out for virtually all the elements in the periodic table, so far as that goes. And so there is an availability, but it's also another thing you learned in your earlier studies, not in high school, but called entropy. How concentrated is that stuff? Okay, gold is valuable because we measure the ores in ounces per ton. Okay, ounces of gold per ton. So If you got to dig up a ton of material to get 3 ounces of gold, it's going to cost a fair amount of money because of all the energy that goes into recovering that. Okay, but in addition, there's another bigger energy cost than just that. It's basically, this is also out of Ashby's chapter 2, approximate energy content of materials in gigajoules per ton. So this is straight out of thermodynamics. Aluminum is 300 gigajoules per ton, and look down here at steel, it's 1/6 of that. So the people who like to think that someday aluminum will be as inexpensive as steel are kidding themselves. Because you can go back to thermodynamics, and iron oxide is less stable than aluminum oxide. It's always going to cost more to separate that aluminum from its oxygen than it will to separate the iron from its oxygen. And in fact, well, we can talk about other things, but copper here is 100, not because it has such a stable copper oxide or copper sulfide, but in fact, it's not found in ore. The ores are not very rich. I mean, there were ores in the Congo, which is Zaire now, that were 2 or 3% copper. But we sort of mined those out. And now we're dealing with ores that are 1 or 2 pounds per ton, okay? Or maybe 10 pounds per ton. And so, again, it's sort of like gold. Now, there's a nice little rule of thumb that I use of the difference in price between gold, silver, and copper. They're right next to each other on the periodic table. I don't know if I should have a periodic table here somewhere. But does anybody know what the relative price is between those? What's the price of silver compared to copper? What's the ratio? It's about a factor of 100. What's the ratio of gold to silver? It's about a factor of 100. So that means the price of gold to copper is about a factor of 10,000. So if we're talking about price of materials, the number one material, if I was going to select a material to convey water, okay, in a home, the best material would be gold. But we don't use it because it's a little pricey, okay? We use other things. What was the first material to convey water? I mean, water is a pretty basic commodity in itself. In fact, as commodities go, water is one of the 4 basic elements. Did you know there are 4 basic elements? According to Aristotle, there's fire, earth, air, and water. And this all through the thousands of millennia and stuff. The ancients considered fire, earth, air, water, and some people included wind, but others understood wind was just a fast form of air. But in any case, those were the basic elements. And Aristotle, actually, Aristotle drew something like this phase diagram. I don't know if he drew it as a diagram, but fire is both hot and dry. Earth is both dry and cold. Water is cold and wet. Okay, so these are properties. This is the first structure property diagram. Okay, so way ahead of all the material scientists of this century. But anyway, so there's structure and properties, elements and properties. But if we go back to the ancient times, what was the first material to convey water? I mean, water's sort of necessary to drink and things like that. You don't always build your campfire or your bed right next to a stream, and you have to convey water. What do you think was the first material? They had to carry the water, right? You don't want to cup your hands. Think about it, right? Pardon me? Wood. Someone took some old log and hollowed it out, and they had a wooden bucket. And why don't we have any of those old wooden buckets? Because wood doesn't last that long, okay? It rotted away thousands of years ago. But it's most likely they used wood. What was the second material they might have used? Might have been stone and mortar. They may have built a little trough, okay? And in fact, the Romans built, what did the Romans build? Aqueducts. There's actually a recent article in the last 2 weeks or 3 weeks in Science magazine about how the Roman concrete is so much better than our concrete even today. It's lasted better. And so some people have been researching this, and they found it's because they used a particular type of volcanic rock that had certain properties. And so now they're trying to improve concrete today based on what they've learned about the chemistry of the Roman concrete. I guess those Romans were a lot better material scientists than we thought. They didn't have a clue, but anyway, just dumb luck, most likely. In any case, I had some notes here. Where did I put them? About water. So wood, stone mortar, concrete aqueducts. And then in the 18th and 19th centuries, they started using pipes. What did they make the pipes out of? Anybody know? The first pipes for conveying water? Lead. There's lead pipes. This is out of Ashby's book, and he's showing lead pipes, and this is in the chapter on creep. So these lead pipes have been sitting there for several hundred years, and they're noticeably sagging because they're creeping at room temperature. Okay, so they used lead pipes. I actually had, my house is 85 years old, and I had a lead drainage pipe in the laundry room when I first moved into the house 40 years ago. I got rid of it, but I'm not drinking out of that water. But nowadays, they just outlawed even lead and brass. A lot of the brass we use in plumbing, like a fitting like this, 10 years ago would have been made out of a leaded brass. Can't do that as of next year. Okay, they're going to have non-leaded brasses. Anybody know why we use leaded brasses? Okay, turns out when you machine a leaded brass, the lead doesn't mix with the copper and zinc. It forms little islands, inclusions of lead, and when you machine it, the lead heats up, melts, and forms a lubricant. You can machine brass, leaded brass, about 5 times faster than regular brass. And so it's cost again. Okay? We used to use leaded brass, and we never thought that the amount of lead leaching out of the water was turning all those children ignorant. Okay? Well, in fact, it wasn't. It was genetics that made them ignorant. Okay? But mom and dad don't want to think that it's their genetics that made their children ignorant. They want all the lead out of the system. And so in 1978, Massachusetts outlawed lead tin solders. And so now they only have tin solders for making plumbing. But in fact, we all think that copper pipe was the way to do plumbing, but it turns out it wasn't. I mean, in the 19th century, we used lead pipes. And some people would use steel pipes, but then you get rust, and your water was brown. And it doesn't hurt you because it turns out iron oxide is the non-toxic control that the toxicologists use. You can drink iron oxide, it won't kill you. When they try to kill the rats, the control thing, when they have them breathe fume and stuff, they have them breathe iron oxide fume for the non-toxic control. Okay? So iron oxide is not toxic in the body, according to the health scientists. But in any case, they didn't like to use straight straight steel pipes, which they had in the 19th century. They used lead because it wouldn't corrode. Anybody know where we have a roof at MIT that is lead? Kresge Auditorium. Thinner than an eggshell in ratio to its radius, but it's actually it's a lead roof, because lead lasts forever in the environment, okay, and atmospheric corrosion. So does copper. But in any case, so there are various properties, but so we used galvanized. We actually ended up using galvanized pipe until about World War II, and then after World War II, we started using copper pipe a lot more frequently. But today we actually use something else. Anybody know what it is? Pardon me? PEX. PEX. Looks like this. Okay? That's a PEX tube with a plastic fitting. This is a brass fitting. This is PEX. I think this is PEX A and that's PEX B. PEX stands for cross-linked polyethylene. PE, polyethylene, and X for cross-linked. There's 2 ways to cross-link it. You can hit it with electrons, And I'm pretty sure that's PEX A, which is this one. I know this is the more expensive one that you hit with the electrons to get the cross links. And this is just like Charles Goodyear and sulfur and rubber. You're trying to make a cross link of your polymer chains to make a three-dimensional structure. I'm getting some nods. Some of you are material scientists and understand those things, right? And then PEX B, they basically do chemical cross-linking, which is sort of what Charles Goodyear did with the sulfur, okay? You put sulfur in and the double bond sulfur ends up creating the cross-link between two of the polymer chains, and you end up with rubber. Well, so they started selling PEX, and there have been hundreds of millions of dollars worth of settlements in Las Vegas and some other places, and there's still billions of dollars worth of lawsuits because some material scientists on the West Coast have determined that this type of brass, the leaded brass, which we've been using for about 100 years, is defective. And they are suing, and all the homeowners whose houses are underwater on their mortgages, this is an externality, okay? They're suing to have the builders replace all their plastic pipe because of these brass fittings. Now the whole thing is bogus. What they're saying is, wow, this stuff dezinkifies. There's something called dealloying, and it occurs in certain waters that are pretty corrosive, like Las Vegas. Colorado river water is not the greatest stuff. And anyway, so they get some dezinkification. Analogous to that in steel is something we call rust, okay? Would you consider any car that had a spot of rust to be defective and should be scrapped? Would you consider any bridge that had a spot of rust to be defective because it started to corrode and eventually will wear away to nothing? Yeah, well, what is eventually? Is it 100 years, 1,000 years? These people are predicting 5-year lifetime in systems that are already 20 years old. Okay, they're saying that it'll fail in the first 5 years, but they've been there for 20 years. Doesn't bother, doesn't matter, okay? So in any case, we've selected materials over the years to convey water from wood and stone and mortar and concrete. We still use concrete to convey water. Great big pipes bringing water from the Quabbin Reservoir to Boston. Great big concrete pipes. They might be encased in steel to give them structural strength, but they often align the inside with concrete because it's very corrosion resistant to water, and just like the Romans learned, okay? So there's material selection issues. There's all kinds of issues in something as simple as conveying water, and price and availability are the number one criteria in selecting any material. It doesn't matter. Every material has a price, but there are different ways to look at those prices. I told you about the abundance and the energy cost per ton, but if you look at some of the reasons why we select materials, and this is supposed to be a course on structural materials. I'm gonna have to do something about that glare. Anyway, cost is the number one object. Strength and fracture resistance, if we're talking structural materials, is the number one thing, or one of the next one. Availability, fabricability, can you join it together? Can you form it and shape it? Can you recycle it? And repairability, can you repair it? And there's a number of great new materials that fail one of these types of things. I could keep on going on this list, okay? Selection of a material is multidimensional. People want to build composite structures, okay? But we don't make that many composite structures, and one of them is cost, and we'll talk about that. And to go a little bit more on cost, if you go back to Ashby, this is sort of stolen from one of the plots that he has. This is the price per ton. In his new edition, he doesn't do dollars per ton. He does, I think iron is a factor of 100, steel is 100, not in dollars, just a relative scale. And diamonds is 200 million times greater than the cost of steel per ton. Diamonds are the most expensive material that we have on a per ton basis, okay? And that's because of scarcity and how they have to mine them and things like that. I actually drew some lines across here, and we'll talk about that in a little bit. But basically, the materials that you can build an automobile with are the materials that fall below the green line. The materials that you can build an aircraft with are the materials that fall below the blue line, and the materials that you might use in a spacecraft are above that line in general. But I'm going to talk about a little bit more about that in a little bit. Now, Ashby developed these plots called Ashby Plots now, very clever designation. And he has a whole book on these. Actually, he has whole books on these. He sells this little book for about $300. And it comes with this book, which is not copyrighted. And this is just a series of these plots. And his $50,000 program is an even bigger program that can generate these plots from the big database of materials. And this is just a way that you're supposed to be able to select a material. This is relative cost per unit volume. So it's cost relative times density, and Young's modulus in this case. And these are useful plots in terms of kind of looking at materials and say, well, what classes of materials have what properties? And in Ashby, being quantitative, being a good scientist, he looks at certain parameters. If I'm looking at modulus per unit volume, it's the modulus E versus divided by the relative cost. And elastomers are way down here. Where would I like to be? By the way, this is to the 1/2 power, and this is the 1/3 power. On a log-log plot, you can put these slopes on here. And for sheets or beams, you'll have different ratios of modulus. The modulus comes into the formula, the bending of a beam formula to a different power, or bending of a sheet. And so you might have different slopes, but obviously you'd really like to be up in that corner, low cost and high modulus, so you want something stiff, okay? And I'll give you an example of that in a little bit. But what do we have? The stuff that's up here at the lowest cost is brick, stone, and concrete. And then over in this corner, we got mild steel. We have engineering ceramics, which are actually pretty pricey if they're engineering ceramics. Now, the cheapest ceramic is concrete, okay? And so it's way over there. So ceramics go all the way across there. Woods actually are pretty good as structural materials. These are foams. Now, this is interesting in here. Polyfluoride. Yeah, it's Teflon basically, which is fairly stiff. Things like KelF and stuff. High density polyethylene, low density polyethylene, hard butyl, soft butyl. It's all vertical here. All these plastics. There are all kinds of engineering polymers. Some of them get pretty pricey. This is Teflon actually. I'll have to check and see what PF is. Anyway, there's your plastics. Here's your composites. Here's your metals. Here's your stone and brick. You can kind of class these things in certain property areas, which is what you as a designer, if you're selecting a material, want to know about. Can anybody figure out why these are all lined up, these common commodity polymers? What are they lined up? What axis are they lined up with? Cost. They all have about the same cost. Why? Because their cost is basically the cost of the energy they supplanted. How many barrels of oil does it take to make how many pounds of polyethylene? It's about the same for polypropylene. Not a lot different. So all these sort of, it follows a trend, but you can get a different modulus, okay? The butyls are basically rubbers down here, okay? So the modulus might be different. The woods are a composite material, so it depends on whether you're parallel or perpendicular to the grain, okay, here and here. But you can look at a lot of different parameters on an Ashby plot. And basically, he started out in the 1980s doing these plots in 2 dimensions, and his computer program takes these to 3 dimensions, okay, or more dimensions. So you can look at 10 different properties at a time and come up with some value product of that. Those are things that experts used to do in the past. If you look at strength, which for structural materials is a pretty important parameter, and we look in strength versus relative cost, again, we want to be up here, and we've got brick, stone, and concrete. But among the ductile materials, mild steel and glasses are way up here. Your engineering ceramics are way back over here, which is a bad thing. You really want to be above this line over here. Your plastics are down here. So by looking at a plot like this, you can conclude something that a few years ago the US Navy spent $1 million to figure out. Okay? Actually, no, it was the US Army. The US Army did $1 million study to figure out, this is about 15 or 20 years ago, what was the material of the future for the US Army. Okay? Because the Army buys billions of dollars worth of ordnance and materials every year. And if they could figure out what the material of the future would be, it would give them a significant advantage and help them to figure out where to spend their research money. What was the material, what did they conclude? Now you know, I just told you. Steel! Okay? Why steel? Well, it turns out, if you look at combinations of mechanical properties, steel is the cheapest that has the highest strength and the best toughness. And you need toughness to defeat weapons coming in. You need strength to make things relatively lightweight. Although you can make them lighter weight with aluminum, but you sacrifice some of your ability to protect against the armor is not as good. But it turns out they spent $1 million trying to figure out what the material of the future would be, and it turns out it was steel. And I remember 25 years ago, I was going around giving talks because in the mid-'80s, the ceramists were touting that ceramics were going to take over the world, that ceramics had much better properties. The problem is the ceramist had never studied mechanical properties very much because the mechanical properties of the ceramics are pretty lousy. We'll talk about this more, but this was June 1991. I finally wrote a paper on this called The Future of Metals. And the first plot that I had in that paper was this one, which is out of every 100 pounds of metal made in the world, how much is what? And it turns out over 95% is iron and steel of every 100 pounds of metal. And less than 2% is the number 2 metal, aluminum. Today we make about 1 billion tons of steel every year in the world. We make about 40 million tons of aluminum. Okay, or is that right? Maybe it's 20 million tons. But anyway, copper is number 3. Zinc is number 4. It's mostly used to protect steel, okay, from corrosion, which is one of its Achilles heels, so far as that goes. But it turns out steel for structural materials is the material of choice because of all those properties we talked about before. If you start looking at these things, cost, steel is one of the lowest cost structural materials. 20 cents a pound, folks. Strength and fracture resistance. If I put up the Ashby plot for strength and fracture resistance, steel is way up there. One of the best, unless you're going to cobalt and nickel-based superalloys for jet engines, which cost not 20 cents a pound, but $100 to $200 a pound in many cases. Okay, so there's a price difference, and when you look at cost and price, why don't we build railroads out of nickel? Well, first of all, we don't have enough nickel in the world. The availability is such that you couldn't do it. In fact, at one time they were talking about making a higher quality pipeline steel that was going to have 2% nickel, and they were going to use all the world's nickel per year in building that pipeline. Okay? Even just 2%. of nickel in the alloying with the steel was going to consume all the nickel in the world. So they decided, well, maybe that alloy was a little too rich, okay, for that application, okay? So it's an availability. Fabricability, steel's one of the easiest things to join. Recyclability, steel's recycled at about 70–80%, okay? Why? Well, when you're producing 1 billion tons, you're going to be bringing back about 500 million tons a year of scrap. And if all you're going to do is let it sit there and rust, that's sort of a waste, so we know how to recycle. Aluminum is recycled at about 50 or 60%, but not as high as steel. The most used material, or man-made material, is not, well, I'll tell you what it is in a second, but it's something we don't recycle. And we make 1.5 or 2 billion tons a year, and we don't recycle it, and it's going to be a bigger and bigger problem. If you can figure out that problem, how to recycle it, you'll become a rich person. Anyway, a lot of people knew about this magic behavior of steel. A guy named Rudyard Kipling said, gold is for the mistress, silver for the maid. A little sexist here, but anyway. Copper for the craftsman cutting at his trade. Good, said the baron sitting in his hall, but iron, cold iron, is master of them all. Okay? So you're going to find Tom Eager keeps on talking about steel. Okay? In this paper I just handed out, The Future of Metals, I basically said, you know, you can talk about fine ceramics and it's going to be a $100 billion industry. This is what people were predicting in 1990. You could talk about composites and it's going to be a $50 billion industry. You can talk about silicon and it's going to be a $100 billion industry. And I said, if you take all of them, the growth of all of those businesses combined, it's not as big as the current market for steel, which at that time was $500 billion a year. It's about $1 trillion a year now, okay? So who was the richest man in the world in 1880? And what did he make his money on? Today, well, you know, Bill Gates became the richest man, and I don't know, some guy, Carlos Slim or whatever in Mexico, probably made it on drugs for all I know, but it's a material of choice. But anyway, Andrew Carnegie was the richest person in the world. He made it on steel because of the railroads. So steel, I mentioned before that steel is a fundamental material to all the infrastructure. Before the Arab oil embargo in 72, steel was the material that controlled the world's economy. Oil became the thing after that. And oil is really just the surrogate for energy, whether it's wind energy or hydropower or whatever, or nuclear energy. Oil is a replacement for those, and as the price of oil goes up, the value of a nuclear plant goes up. Okay, they're all tied together because we have ways to exchange energy. It's fungible in general from one material to another. Okay, any questions on that? That when we're talking structural materials, iron is the most important, but you can't use iron in all applications. Iron will just doesn't have the strength at high temperatures. It doesn't have the corrosion resistance. And sometimes you have to use something that costs 100 times as much or more because you need those other properties. And we'll talk about some of those things. But you can also talk about materials as two types. I'm going to go back a little more general. And the Japanese in the 80s started talking about functional materials, okay? And they were all excited about functional materials. Fine ceramics were functional materials. You could make knives out of them, kitchen knives. I mean, I have several ceramic knives in my kitchen. Great for cutting onions. Anybody know why? Because they don't crush the cells and let out all those juices that make you cry. The ceramic knives stay sharp and they slice the cell and they don't release as much of the juice and you don't cry as much. It's true. So you can spend $100 for a ceramic knife. And if you're careful, it won't chip, okay, and lose its sharp edge, okay? But nonetheless, so there's certain advantages, but that actually is a structural material application. But of all those billions of dollars that were spent on structural materials or structural ceramics, if all we can talk about them now is kitchen knives, okay, there's got to be more to life than kitchen knives. But functional materials is what we read about all the time. And why am I one of the last dinosaurs in this department that knows anything about structural materials? Because everybody works on functional materials. But that's not what the world is made out of. The world is made out of structural materials. I remember when they were trying to get the biology option for freshmen, they're going to take away the last remaining elective in the freshman year, and you're going to have to take biology. And the associate dean was trying to convince me at a dinner that we should give up any electives in the freshman year and start requiring biology. And they eventually did, and it probably was a good idea. And they forced me to spend a week one summer taking a biology course from a bunch of Nobel laureates, Philip Sharp and David Baltimore and a couple of others. Taught me molecular biology for 1 week for whatever that was worth. But anyway, I mean, I haven't done much with it, except I now can argue with my medical doctor when he tells me to lose weight. Of course I should lose weight, but anyway, never mind. Anyway, there are lots of structural materials, and the thing about structural materials, they're used in very large quantities. And if you take my processing course, which is one of the other options, I will make an argument of why nanomaterials will never be structural materials. And all it just happens to, I'll tell you the bottom line, processing rate. To make nanomaterials, you basically have to make them from the vapor phase, and you can grow them at a millimeter per hour. This is based on the kinetic theory of gases and how fast the vapor phase can condense, okay, to make a solid. Whereas structural materials, if you cast the material, you can cast the material with a flux of atoms going into the mold that's 100 million times greater than you can do with vapor phase processing. Now, that's not to say nanomaterials won't be important as functional materials. They will. But as structural materials, I mean, I've had this debate with your thesis advisor who's trying to make carbon fibers, and I told him, if he can get the cost down to $2 a pound for carbon fibers, you know, Bucky fibers or whatever we call them, then he might have something he could make a composite with. But at $10 to $15 a pound, I told him it's not going to work. So last time I saw him, he says, well, he's getting it down. You know, he's down to about $6 or something. Okay, good. And maybe he will, but in 1991, I would go around the country and telling people that steel was an important material, and people were saying, we won't be using steel in automobiles in the future. It's all going to be aluminum or composite or plastic. And I said, no. And I said it based on this idea of cost, which is what we're supposed to be talking about today. And everybody thought I was a Luddite, okay? Who would think steels 20 years from now would be the primary material in an automobile? And that is what I was predicting in 1991. I just wish I had taken a few bets on it. I offered to make bets, but no one would give me a bet, okay? I would have won the bet. Go look at the cars today. Yes, you can. I used to say at the time, yeah, you can buy an all-aluminum Audi. We had all-aluminum Duesenbergs in the 1930s. But we didn't sell them for, you wouldn't buy a Ford Taurus for $20,000 if it was made out of aluminum. It would be a $40,000 Ford Taurus, okay? And Professor Clark had students doing doctoral theses on substitution of aluminum, making a Ford Taurus out of aluminum. And concluded that it only cost $500 more. And I said, what about fabricability? And she had to go back and rewrite another chapter, not a chapter, but a page in her thesis. And she still didn't get the point. But there's reasons why cars and ships and railroads are made out of steel, and airplanes are made out of aluminum. And we'll go through that in a little bit. But you need to understand there are different properties. Structural materials, we have mechanical properties, which have all kinds of different properties. Functional materials, we have chemical properties, magnetic properties, all kinds of things. Here's an example of a catalytic converter. A ceramic substrate to take the platinum or palladium catalyst. Here's another one. Only this one's made out of metal. This is made out of a high temperature metal, because the problem is you got gases going through here at above 2,000 degrees. Most metals are going to oxidize and melt. So So they have to use a ceramic, which has high temperature capability. This is the type of catalytic converter you have in your car. It's made by Corning by an extrusion process, very proprietary to get thin walls. This, if you pass them around, a lot of the weight, of course, this is the outside steel case, but that one is made out of a iron, chrome, nickel, aluminum, yttrium alloy, which is type of the coating they put on turbine blades, and they roll it into sheet. Very expensive, but it turns out at one time they were looking at a lightweight catalytic converter substrate, which in this case could have been a rolled metal like that, because most of your emissions occur on startup before the catalytic converter, this big heavy one, gets to temperature. It doesn't work until it gets hot, and when you start your car and drive away for the first couple of miles, that catalytic converter is not working. Anybody get their car inspected? They tell you to run it for 20 minutes before you go in. Why? You'll flunk the emissions test. Your catalytic converter is not operating because it's not warm yet. Okay? That thing will heat up in about 1/5 the time of this one. You can pass that one around if you want, if anyone wants to look at it. Okay? But you can just feel the difference in mass between the two, which comes from different things. But anyway, there are structural materials and there are functional materials. We're going to talk about structural materials, and now I'm going to hand out something that doesn't have my name on it, but I did write it. I was on a committee for the National Research Council a few years ago that was supposed to be looking at where the Defense Department should spend their money in the future on materials research. And so it has this catchy title of Materials Research to Meet 21st Century Defense Needs. And I was on this committee with all these people who were telling me about all these wonderful new materials that I knew wouldn't meet the cost criteria. And there are like 40 people on this committee, some of the top scientists and material scientists in the country. And frankly, I was sort of a fish out of water because I had a different philosophy about selection of materials. And I knew that the Army had done this study and concluded that steel was the material of the future. They were telling us about fancy composites and all these other things. If you want to know what Tom Eager thinks about selection of materials, this is what I wrote up based on what I was teaching in this course into 4 pages. Here's the summary of this week's and next week's lectures from me. Okay? So if the only thing you read is one thing, this is what you ought to read. But in fact, in here, I'm not going to go through and use all of that. I'll do some other things. I go back to something a guy named Jack Westbrook, graduate of this department, put together when he was at a company called General Electric Research back in 1962. And this is his plot from 1962 on structural materials. Okay, there's another copy of this in there, but this is pounds per year used on a log scale going up to 10 to the 12th pounds. And here's dollars per pound, but it's 1962 dollars and stuff. But anyway, what's the most used material in the world? Stone. Take a rock and you crush it. Okay? And you'll find the price is about 10, 20 cents a pound. Okay? For crushed stone. Maybe less, maybe even 5. Depends on where you get your stone and what type of stone. The number one process material is something called cement and brick. And wood is in there. We use a lot of wood. Okay? These are not fancy materials, but they're the most used materials. Steel is up here. Carbon steel is way up here. And you look out here, here's diamonds. And basically, this is a 2-dimensional plot. Ashby gives you a single-dimensional plot of cost, okay? And this is similar to Ashby's table of cost in his chapter that I passed out. But this just tells you what's used and at what rate. The interesting thing is Jack Westbrook put these dashed lines on here. Those are ISO market size lines. And the interesting thing about this plot that I figured out was that if I can reduce my cost by a factor of 2, the slope of this usage plot is steeper than the ISO market line size. So if I reduce the cost of a material by a factor of 2, over the long run, economically, I will double my market, because this slope says for every factor of 2 reduction in cost, you'll get a factor of 4 increase in volume, according to the slope of the line. So if I get half as much, but I sell 4 times as much, my competitiveness just doubled, right, in terms of market size. So cost is a very important thing in materials processing, in selection of a material, in growth of markets, and things like that. Okay? Now, what's the material that I said we make 2 billion tons a year and we don't recycle? Well, steel's 1 billion tons. What's up here? There's only a couple of choices. Well, we don't recycle stone. Actually, we do sort of recycle stone, but a lot of the stone goes into something that we don't recycle called concrete. And we're building concrete roads, dams, all kinds of things out of concrete. And a lot of the concrete has sort of a 100-year life, and we haven't really seen it come back in recycling yet. But there are parts of the world where they do use concrete a lot, and it is starting to come back. They have an earthquake in certain areas where they don't design for it. All of a sudden, they got lots of concrete to recycle. And a lot of them just dump it in, you know, extend the shore out a little further. And maybe if the oceans are rising, we will have a good use for concrete as dams to keep the ocean. I don't know, but 2 billion tons a year? We recycle 70% of our steel because we have to. Okay? Economically, it makes sense. But if we didn't, we'd be buried in mountains of old rusty steel. We recycle most of our aluminum. Why? Or not as much as the steel. Why? Because aluminum is canned energy. I showed you aluminum's got one of the highest energy costs per pound of material. You can get a lot of energy by just remelting aluminum as opposed to extracting it from its ore. Okay? And more, these metals industries that have been around for 100 years, we're not going to be using as much virgin iron ore and as much virgin aluminum ore. We're going to be doing recycling. We're going to get to something more of a steady state where most of our materials are recycled. It's because of this growth over the last 150 years of the metals business, which Ashby will point out has been growing exponentially, if you read his chapter. Okay? But that exponential growth is going to start to flatten off. The world is only of a finite size. And as it starts to level off, and we've been putting about 500 million tons of steel into the environment every year for the last 100 years. And some of that has come back, but it's going to keep coming back, and we're going to get to a steady state eventually where the recyclability starts to be a constant fraction of the use. The use won't keep growing exponentially. Okay? It's called a sigmoidal curve, and we can get into that if you want. But anyway, this 1962 plot of Westbrook is very important in understanding materials. Now, the other thing is, I hate to dash your hopes as young budding material scientists, but the actual, oops, I gotta get out of here. The actual cost of materials is a small fraction of the manufactured cost of a product. The cost of materials is only about 10% of the cost of the product. And on next Tuesday, Dr. Belmar will be lecturing tomorrow and on Monday on his section of the course. But next Tuesday, I will explain what makes up the other 90% of the cost of a product that you sell. Most of it is in processing, inspection, marketing, fabrication, things like that consume most of the cost of what you're building. And therefore, if you're paying 20 cents a pound for steel, your structure, whether it's a bridge or an automobile, is going to cost you $2 a pound for the steel that you're actually using to actually make it into a useful shape. So the big costs are actually in the productivity of turning it into a useful product. Okay, I got to get, well, actually, I don't have that other class on, except Mondays and Wednesdays.